Welcome to the Mound Cold War Discovery Center, and this is our monthly Mound Science and Energy Museum Association seminar series that we have been presenting for pretty close to 20 years, off and on, most regularly. And so we cover historical talk, technical talk. Today we're going to have a nice technology talk by Dr. Jim Van Wert. He actually has two businesses on site here, so he's part of Mound Business Park. And so rather than take any of his thunder, I'm going to let Jim start.
Well, first of all, thanks very much for coming. I'm always in awe every time I meet, the Bobs and the Dougs and Jacks and everybody else. It's the guys that worked at the Mound. You guys did some amazing things, and it's always exciting to listen and talk. And I'll never forget the one comment that Bobby said. So yeah, that's a Mound technology. We did that forever, and I loved it. So today, what I'm going to talk a little bit about is thermal diffusion galvanizing. It's a process that's been around for 120 years. It was first patented that long ago, and I'll cover a little bit about it. We'll go through in more in depth. What I did is a company reached out to me and said, hey, we're having to pay a lot of money for powder, and the process is not very well controlled. Can you help us? I really didn't want to do it because I'd retired 3 times already. And so I wrote a proposal, and like some of you have done proposals, I made it really fat. And I thought, they're never going to accept it. Well, I was wrong. So, with that introduction, this is kind of what I want to cover. And I always try to do my PowerPoints with what are we going to see, what are we going to talk about. So, what is thermal diffusion galvanizing? Why is it important? The history of it, corrosion resistance of it, and that's really why it's done. But there are some other things that are pretty interesting. Mechanical property improvements, how is it applied, and then some typical applications. I've got a few things that were easy to carry that I put up on the table up here that you're more than welcome to take a look at after we're finished. And if you have questions, feel free to ask the questions anytime. Yes, sir?
You're going to talk about your symbol?
Yes. My partner and I, we're looking for something to trademark, right? It's something unique. So we said, UltraGal, it's really strong, and it's, a gorilla. So that's how we ended up with our logo. So.
What about the green one?
The green one, it was part of a company up in Holland, Michigan that I own part of now that had started out probably 15 years ago in this kind of process. And when I worked for Victaulic, I visited them to look at them as a supplier. Well, I was the director of global quality at the time, and when I looked at their quality operation and how they controlled their process, I thought, you guys don't know what you're doing. So I started learning more and more about the process, and so I became probably more educated in their process than they were. And so that's how they reached out to me and said, can you help us? So what is thermal diffusion galvanizing? It's a method of applying a uniform sacrificial zinc iron alloy. It becomes a coating. And it's a metallurgical vapor deposition process. Unlike some vapor deposition processes where they're done in vacuums and done in atmospheres and all that stuff, this is not done that way, and you'll see it later. It's very, very interesting the way we do it, and the formula that we created is how we're getting away with it. But you can see, you can apply it to powder metal parts, regular steel, castings and forgings, stainless steel. And you'd say, well, why stainless steel? Why would you want to coat stainless steel for? There's some really interesting things. Some of it's galvanic corrosion, and this can actually end up being an inhibitor between, things where you could have big differential, electrochemical differential and cause galvanic corrosion. So, why do we do it? It's as they say, corrosion kills. Maybe. So, it kills people, and we'll show some examples later. It kills productivity, it kills profits, it kills the environment, appearances, reputations. You know, something fails, it's your reputation. And so this chart, it's old, but it was so powerful, I said, I really got to show this. And so this is the cost of corrosion. And you say, wait a minute. And this is in the GDP globally. And you say, well, how big a number is that? And you look at these numbers are in hundreds of billions of dollars per country. That's what corrosion costs. And so this process is a process to really help mitigate some of the corrosion things that are going on.
Can you give us the word below the bars? I can't read it.
The words below the bars are the different countries. I apologize for the eye chart. So each one is different countries. And then kind of at the very end is, I mean, there are specific like Russia, China, the Arab worlds, you know, India, the United States. The United States is 2.7. And then the numbers below that are in the hundreds of billions of dollars. That's what corrosion costs. So it was really intended just to grab your attention of why is corrosion important? Why is coming up with mitigation of corrosion so important? So you've all seen corrosion, right? You've seen it on your cars, you've seen it on parts, bolts, pipes. I've broken many a bolt where it's corroded, and I start horsing on it and break them off. So here's the history. So this is the gentleman, you know, Dr. Coles. He's really the one that invented the process. He patented the process 120 years ago. And it was originally called vapor galvanizing, dry galvanizing, and then it changed. In England it changed, and they named it Sheridizing. And there are some places in Europe that still call it Sheridizing instead of thermal diffusion galvanizing. And so they changed the name to Sheridizing to kind of, you know, take his name through it. And then it's evolved in that last 120 years with powder formulations, process improvements. I'll show you some of our furnace designs. In our furnace design, the insulation characteristics and things, you could put your hand on it, and it's inside is 430 degrees centigrade, and you wouldn't burn your hand. We've simplified it so the energy to run a cycle is about $6, and that's the electricity and the energy. So here's some examples. 1916, one of the largest Sheridizing plants. General Electric, they were one of the big users of the process. 1918. And you can see some of the old furnaces, and they, in this particular case on the left, they had a continuous oven, and they rolled the barrels, rolled inside that continuous oven. And when you see later in the presentation on our application, you'll see it's probably less than the size of this table. And we have a steel drum that actually fits inside a gear motor that drives it, the barrel to keep the parts moving. And then it ramps up. It's all PLC controlled. It's running right now while we're in here, and we'll go and change it out. So why is it, you know, a technology for corrosion prevention? It's sacrificial. What do I mean by sacrificial? Anybody help me? Doug?
It gives up what you put in.
Yeah, it basically is consumed, right? So in this case, the zinc becomes consumable, and it's anti-galling. So it's similar to cadmium, but as you all know, cadmium is on the no-no list. And a lot of fasteners, a lot of things in aerospace where they used cadmium are gone. They're not allowed to use them anymore. The other,
Excuse me, just real quickly.
Sure.
You talk about sacrificial. I'm still puzzled a little bit by that. You know, we talk about preventing corrosion by basically coating a part with a non-reactive substance
Mhm.
that's not going to oxidize, right? And you say it's sacrificial. I mean, it's a little like cadmium. Cadmium's not sacrificial.
oh, it is.
It is?
Yes, it is. Yeah, and part of how it's protected is because it does oxidize. And in this particular case, it is sacrificial. Let's say if you scratched it, you scratch the oxide off, you'll actually create a reaction, but part of why it's protecting itself is because of the oxide. Aluminum, classic, one of the characteristics of aluminum is it protects itself.
Yes.
Once it oxidizes, it pretty much, you know, they look ugly in your car underneath your hood. Sometimes they turn white, nasty looking, but they protected themselves. The other thing is this coating, because it's semi-porous, when I say porous, more granular, it's very good from an adhesion standpoint. So top coats, which we use, and if you wanted to overmold this with rubber, it works very well for adherence of that surface. For example, one of the applications for Victaulic is valve discs. They use butterfly discs, and some of the discs are rubber-coated ductile liner. Well, they have a really difficult time in coating some of those valve discs because what will happen is you'll get air underneath it, and they'll blister off and peel off. But because of this surface texture, you get very good adhesion. Environmentally friendly. So if you compared this to hot dip galvanizing, have any of you seen a hot dip galvanizing process? It's nasty. In fact, I went to one time in Mexico. As the director of global quality, I was supposed to do an audit. I got close to the door, and I said, guys, I'm not going in there. The fumes were so strong coming out of that room, it was awful. And this particular case, there's no bad byproducts at all. There's there's nothing we have to throw away. There's no bad fumes. There is dust. Gabriel can tell you, he's one of my workers up here in the front. When he goes home in the afternoon, after he works Wednesdays and Thursdays, because he has to go to school the rest of the time, he looks pretty dusty. They actually won an award for the technology in 2006, an environmental award, for being a clean energy, clean process. Our particular process, we talk about made in the USA. Well, we're actually doing it in the USA. We're not going to China to coat it. The Chinese are trying to do this process, but they're not very successful. A lot of when they started this process, it was actually the Russians and the Israelis were some of the ones that were probably making the most progress in the technology. It's heat resistant. So this coating, up to 1200 degrees Fahrenheit, resistant. So it doesn't deteriorate up to that temperature. So it's pretty good. And it's uniformly applied. And so because it's a vapor, if you were to try to plate something, if you're familiar with plating, you have to basically throw those electrons inside, let's say, a tube. You're not going to plate inside that tube very well. In our case, it's a vapor. It'll go all the way around, inside, everywhere. In fact, we did, in this particular case here, it's a nut and bolt. And I said, I wonder if I put that nut on the bolt, would I get coating inside of the threads, inside of the nut? And the answer is yes. So, yeah. So here's a little bit about mechanical property improvements, which you'd say, how is this coating doing that? Well, there's some things that are going on. Have you heard of hydrogen embrittlement? This coating is not susceptible to hydrogen embrittlement. So that's a very good thing. And I'll show you some examples of hydrogen embrittlement in a minute. But you can actually see rigidity, we get some improvement. Yield strength, we get some improvement. Tensile strength. Well, if you take down below, you can see raw steel. What alloy? I don't know. I plagiarized the chart. But we've done some of our own testing with 1020 steels and things like that. And so you can kind of see there's some improvement. The braking elongation isn't as good because it's a little bit less ductile, because obviously there's a hard coating on it. But just in general, we're getting some mechanical property improvement. So this is another really good graph that I liked. And so this is kind of like the salt spray across the top. And you can see the different types of processes and what happens at the various hours. So if you take, zinc flake, for example, zinc flake is almost like a paint that's applied over the surface, but it's a paint, it's topical. And so if you bent it or crack it, it cracks, and so you end up creating holidays inside of that. In this particular case, I'm going to show you an example on a rock anchor, and we've done actually some bars, bent them 180 degrees. We don't crack the coating. Salt sprayed afterwards, and they still pass the salt spray. Yes, sir.
I too can't read as much as this. Could you just either maybe point to point or go left to right? Say, what are the objects represented by these screws, left to right?
So,
Or the processes?
hot dip galvanizing,
Yeah,
okay. Zinc plating,
that's the next one.
okay. And so the zinc flake is there. And zinc flake is, I'm not going to badmouth zinc flake because we've looked at zinc flake, and in fact, the only bad thing with the zinc flake is it's like painting. So if you chip it, you created a holiday, you're going to get corrosion there where you chip it. And then the TDZ, the thermal diffusion zinc or galvanizing, is kind of the bottom.
Oh, well, you stopped partway through. You showed the flake. What's the one to the right of that?
All the way to the right is 304 stainless steel.
Okay.
So where the TDZ ends up is equivalent to 304 stainless steel in most environments. So it's kind of like, wow, can I replace 304 stainless steel with this? In some applications, you can. We've done it.
How about cost?
We're a fraction of, if you take a bolt that's TDZ and a stainless steel bolt, we're 1/5 the cost.
Wow.
It's very attractive. We just did some bolts. That's what that big kind of fat bolt that's sitting on the table. Those are culvert bolts where they bolt the culverts together under roads and things like that. This part here, it's a forging machine. We run it through our process, and it's an L bolt for utility. It's Western utility. It's so cost effective. Our customers in California. We're actually, it's forged in Chicago, coated here, and we're shipping it all the way to Laguna Hills, California. Now, a big need for it because one of the things that's happening, obviously they had a lot of fires out there. They had lots of telephone poles burn up and lots of utility hardware. I received today, we shipped out an order. We got 2 more orders in of this. And then I got notification that they're sending me 2 different other kinds of parts.
When you have a nut and bolt and you torque that, don't you abrade some of that
No, because it's hard enough, and I'll show you in a minute. Good question. It's actually it's diffused into the part. Okay, so 30% of the thickness of the coating is actually into the steel or the iron. So it isn't, it's a metallurgical bond, and I'll show you a little bit about what that looks like. Good questions, thank you. Again, here's a comparison. Electrogalvanizing, you can see the graph, 450 hours at the bottom. The hot dip galvanizing is about the same. Even hot dip galvanizing, I've seen a whole lot less. You look at guardrails and things like that are out there, they're already corroding it at all the interfaces where the bolts are. The TDZ, the only downside is a lot of the capabilities aren't, we don't have a big enough oven to be able to process some of these large parts. That's the one limiting factor in some of these. Now there is a place in Monterrey, Mexico that's doing things for the oil and gas industry, and they've got a 40-foot long oven. And so they're doing pipe in there in a 40-foot long oven. They're buying our powder. They were trying a bunch of different powders. They didn't have the success, and we sell them powder. We actually make more money selling the powder than we would applying the powder to the parts. So here's some examples. Is everybody familiar with salt spray? Yes? No? Bob, so what salt spray is, think of an environmental chamber, and you dial in a certain percentage of salt, and it's controlled by an ASTM B117 specification. And so you hang the part inside or set it onto some plastic rods, and it continually applies a salt spray. And so you monitor it hour after hour, and what it's trying to do is replicate years of service, of life, in a shorter period of time. So, you know, if you take 3,000 hours in a salt spray, that's equivalent to 30 years. So that's kind of what, you know, we've done some fasteners, some things like this, where we'll hang them in there. We have one right now. The company's name is A.Y. McDonald. And one of their businesses, they're a billion-dollar company. One of their businesses is gas meter systems. So for commercial and residential gas meter systems outside of your house, the meters, they decided that they want the meter not to corrode and last the life of that meter. So they challenged us and said, in order for us to do business with you, and they came to see us, and I made a presentation, and they flew their corporate jet, and they had all their 6 or 7 engineers, and they were, you talk about grilling somebody, they really worked me over. And I said, I don't know if we can do it. I said, we've never done it that long before. I said, but let me modify the formula a little bit. We made some changes, and we were the only ones in the country that were able to pass their 3,000 hour specification. So some of those are these right here. These are the nuts. They're kind of like a union nut that connect the meters and connect some of the joints and things like that. We've done, Gabriel, probably 150,000 of them already. I didn't even think there were that many gas meters in the country, you know. And we just got an order for 34,000 more today. So here's some more examples of these are Victaulic bolts and fittings. So this is 2,000 hours. We thought, wow, 2,000 hours, we're heroes, you know. Now, we had A.Y. McDonald on the phone last Thursday, and we're working on another new product for them. And they said, well, the samples you provided, they're still in the salt spray at 3,500 hours. So we've hit a new benchmark. So here's the one I was talking about. So if you did this with paint or any kind of plating, it would crack. So what this is a rock anchor. It's 20, they're normally 20 feet long. And what we did is they're formed, as you see up in the top photograph on the right. And so what we did is we went inside and opened it up and then put it in salt spray. So we unfolded all of that deformation that was there as part of their rock anchor and then put it in salt spray. And we went 1,000 hours. So it's got a lot of ability to you know, take a lot of flexing and bending and those kinds of things. So here's hydrogen embrittlement, and it's really a phenomena when you talk about heat treatment and things like that. It's one of the things where the metal loses ductility and it becomes brittle, and it's partially because it absorbs hydrogen. And that leads to cracks and failures. And one of the ones that I found that was really interesting was the San Francisco-Oakland Bay Bridge. The fasteners and some of the structural parts of why that bridge failed was because of hydrogen embrittlement. And I've experienced it at Victaulic. We had valves and we had the actuator handles and little small fasteners, but they were zinc plated. They weren't properly heat treated afterwards and things like that. And the heads popped right off. And not under any kind of load or anything else. They were sitting in the packaging waiting to be installed on a valve, and the heads all popped off. That was pretty exciting and scary because all these valves we had out there, they're like, oh my God, now what? So
Was it in China?
they were made in China. You're exactly correct. They were made in China. And I ended up having to go there to figure out what was going on. It's a company called Year. Big company. They do a lot of automotive fasteners. And they skipped a step. They skipped a step. Obviously trying to reduce costs, skipped a step. So one of the nice things about our coating process is, versus a lot of other coating, hot dip galvanizing is susceptible to hydrogen embrittlement. Ours is not.
So Jim, is your coating a diffusion barrier?
I wouldn't call it
You
a...
can't get to the steel?
Yes. Yes. And Joe, I'll show you in a minute what the metallurgy looks like and what the coating looks like. And then we use some sealers on top of it. But wear performance, one of the other things that's unique about the coating is its ability for wear. Because of its toughness and the wear and the hardness of that surface, it wears very nice. And we've done a lot of testing where they do wear characteristics and things like that. And this happens to be threads, and you can actually see the uniformity of the coating. And I've got a better picture in the next one, I think. It's coming. So how is it applied? Joe, to your point, the zinc atoms actually transfer and replace the iron atoms. And so when you look at the metallurgy, and I'll show you, there are multiple phases. The outermost phase has about 7% iron particulate in it, iron atoms. That's why we use a sealer on top of it, because you would get what we call blushing, and you'd say, oh my gosh, it's corroding. Well, it's those small amount of iron particulate that actually starts to blush. It isn't the substrate that's corroding at all, but if a customer looked at it, they'd say, oh my God, it looks, it's corroding. So we use a sealer that we developed on top of it as well. The other thing is thickness. If you ever looked at a hot dip galvanized part, it's got drips and runs, and it's very not uniform, right? In our particular cases, we can dial in exactly what the thickness is. You want 7 10,000s? I'll give you 7 10,000s. You want 6,000s? I'll give you 6,000s. We can dial that in, we check, so every load, and Gabriel can tell you, the barrel's opened up, what do?
Test the basis fit.
Yep, we take two out, we wash them, we take them in, we check with an alcometer.
What's that?
An alcometer basically, a lot of coatings can be measured in lots of different ways. One of the problems with our coating, because of that 7% X-ray, for example, the density is too uniform. With steel, you'd never see anything. So it's very difficult. So this is a magnetic resistance, and so it as you put the probe on it, it's bouncing that surface, and you can look at the resistance between the substrate material and the top of the coating, magnetically.
What's the life durability depending on the thickness?
Obviously, the thicker you go, the longer the durability and the longer the life.
And the more you pay for it, the more thickness?
Absolutely, yeah. Because it's two things. It's time and the amount of powder that you put into the barrel with the parts. Not a lot, okay, but it is a higher cost.
Yeah, I know you said diffusion keeps it uniform, but it's hard to understand that with all these different geometries, these parts.
Well, it's a great question. There's a slide coming that's going to show you something that I didn't think was possible. So we're working with a company right now, can't say their name, but they do deck screws and fasteners. And you know, a lot of those have those special bits that drive the screws in. They said, okay, we want to be able to coat the inside of that recess uniformly. I thought, oh my God, there's no way. We're not going to be able to do that. So,
So Jim, is zinc a BCC structure?
yes.
Like
Mhm.
steel? Okay.
Yes. So here's the process flow. Parts are loaded into a steel barrel or drum. We put a special formula powder in. Based on the surface area, how many pieces you have in that drum is how much powder we put in. We've learned a few things about that. Powder is, in some cases, very, very fine. So it's nanoparticle powders in some cases. They like to clump together. So one of the things that we do is we use aluminum oxide. We add some aluminum oxide in there to keep the powder particles separated and distributed inside of the barrel. Doug knows this story, but I was on Facebook Marketplace. I'm a wheeler dealer, always selling stuff or looking for stuff. Well, there was this guy selling aluminum oxide. I thought, wow, we pay 75 cents a pound for aluminum oxide. It's a company in Dayton that actually cleans titanium medical parts and things. And part of their spec is they can only use that aluminum oxide one time. So it's in their blaster once. They can only blast it once, and they got to throw it away or sell it. Well, they had just tons of it, literally. And I was able to go in and wheel and deal and talk to them a little bit. And over time, we started paying 30 cents. Remember, I was paying 75, now I'm at 30. Today, I'm at 12 cents. And it's virgin material. I mean, it's used once and works great. So we're always looking for ways to reduce our costs. And
Your formula for the powder, is it patented or is it a trade secret?
I kept it as a trade secret.
That way, so you don't make public, other people don't know.
Yeah, because
You're the
it's
only
too,
one that has that.
right, it's too easy for people to take patents, because I have 69 patents. Okay, so I know all about the patent process, and there's companies that are just enamored with, oh, we got to patent it. All you've done is tell everybody where to kind of go, right? Okay, well, I'll change this a little bit, and I'll change that a little bit, and they're in the ballpark, right? My case, I said, we're not going to do that. We're going to keep it a trade secret, you know, and that's how we've been successful. But we solved a lot of the things with our formulation of our powder for example, we can run at a lower temperature. Why is that important? Well, energy cost, one. The other is cycle time. It takes less time to get to that temperature. It also takes less time to cool down from that temperature. So it increases productivity. And so our cost for powder, I'll give you an example. A lot of our competitors are $15 to $20 a pound. It cost us $3 a pound to make our powder. We sell it for $7. And we're still way under everybody else's, and it performs better. Yes, sir.
Do you have to pre-clean the parts before you put them in the?
Yes. Depends on the quality. Some of the parts, for example, some of those L-shaped bolts, the forged ones, they came in this week, and they were drenched in oil. And our parts washer wasn't working quite right, the heating, so I had to make a homemade washing machine. And so we did, and we washed the parts with simple green and water and rinsed and spin dried them. And by golly, they worked. So, but today we got an order in, or parts to coat. They were great. So I don't know what's happening at this Ford shop. This Ford shop is out of Chicago, and they've been in business 90 years. So, but yes, we may have to blast. That's what Gabriel did for the majority of the day today, is blast parts. Some of the foundries don't do a very good job, and they leave residue, both the resin residue or sand residue, and we'll blast them and clean them up. So I'll get back to the process. So the barrel's sealed and loaded into the oven. We go through that diffusion cycle. Once that cycle is done, and it rotates while it's going through the oven. And so then what we end up doing is it has to go through a cooling cycle to keep rotating with no temperature input. And why do we get by with $6 of energy? Because what happens is once we get to temperature, it stays there. Our insulation characteristics are so good that the oven doesn't lose heat. And so we don't have any more heat input.
Your powder, when it's in this diffusion cycle, it vaporizes, the powder vaporizes?
Yes, it does.
So basically you have the parts in a vapor?
Yes.
And the drums rotate?
Right. And then one of the key ingredients to the powder is, because if you think about it, if I just put zinc powder in, what would happen as I started to heat it up? Anybody?
Fuse?
No, what's going to happen? It's going to oxidize, right? It doesn't work anymore. So what I had to come up with is, how do I protect that zinc as it goes to that temperature where we get the sublimation temperature and the diffusion? I've got to protect it from oxidizing. That was the trick.
It sounds like you said the barrels are rotating. The parts presumably are tumbling around in there, so there may be some parts that are just not able to withstand that or tangle up or something. Has that been an issue?
Yes, it is. And it depends on the part.
Yeah.
What we've done is put a divider inside to kind of keep them. We've put fixtures inside to do some things to try to control them. Because you don't want, if you can think about something that's threaded, you don't want them, banging onto each other and damaging threads. That's the other portion of why the aluminum oxide is very important. It provides some cushion inside there, keeps things moving around and semi-protected.
Is there any atmospheric issues, like you flood the barrel with nitrogen before you seal it? Or
I haven't had to do that. We've thought about, what if you had, sealed it up, but as you're heating things up, one of the things you have to be cautious of is, do I create a lot of pressure inside? And then I'd have to have a pressure relief valve or something. And in this case, I use an aluminum gasket on the seal. It's not a perfect seal, and it allows a little bit of that to escape. And that seems to be good enough.
So do you just trap air when you seal the barrel itself?
Yes.
It's just air?
Just air. And so then what happens as it starts to vaporize, Bob,
Yeah.
it's taking care of the air. So that becomes more of the vapor inside. And
Displacing
displacing
the air,
Yeah.
like steam.
Are you coating the down every time you do it?
Yes, we are.
What do you do? You take that.
At a certain point, maybe 100 cycles on a barrel, you may have to go in and sandblast it. It doesn't hurt anything, you know, obviously. And once you put a certain thickness on, I mean, it's very difficult to diffuse into.
What was the average thickness that you put on these pipes?
Anywhere from 30 microns to about 70 microns. So not a lot. I mean, so the barrels removed from the oven, the parts are emptied into, there's a couple different ways, but we have a vibratory bowl where we can dump them in. It kind of washes them. They come out, they go into a basket. And then we'll wash the parts, just rinse them, just to get the dust off. The next step is a zinc phosphate. So we'll take them into a zinc phosphate. The pH is about 2.8 in that. Bring it up out of there, bring it over, again, rinse it. And we've come up with an evolution here probably in the last, Gabriel, 3 months, where we had a lot of cycle time where we were having to take it out, spin dry it, put it back. We've created a monorail. So I started thinking about, what if I heated the water? So we heat the water, and so what we're actually doing is we're flash drying the parts. So we dip in the hot water, come up, blow a fan on them, it flash dries them, I can move on to the next operation. So it saved probably 30% cycle time. So we you know, you gotta keep thinking about what can you do different. So zinc phosphate, rinse and dry. We'll have top coats. So I named one of them an ultra nitra, which is a chromium nitrate, cobalt nitrate, water kind of coating. And then the Ultraflex. Ultraflex is a silicate-based coating. So it's similar in nature to a concrete sealer. Very flexible, very low cost, but our competitors were selling it for $90 a gallon. I make it for 12. Okay, so. And then in some cases, the top coats, if you want to, they'll air cure, but it takes time. But if we have to ship something immediately to the customer and they're going to use it, we would cure it in an oven.
Could you mention some of the interval time periods for each of those processes as you go through?
It depends on how fast Gabriel can load on part one, how fast he can load that barrel, okay?
Is the diffusion cycle the long?
It is. I'm being facetious.
That's okay.
He's here, so I got to abuse him, you know? But we're working on, our next step is, I'm looking at a robot to load the barrels. I'm not going to replace him though. There's too many other processes that we have to have somebody move, but it's a lot of work. It's hard work. It's, heavy work. He's got to count. And he's got to count those parts each time,
This looks really complex. I mean, it almost looks like alchemy more than chemistry.
To a metallurgist, that's the sin, I'm just kidding.
You got some magic here that you're not explaining. How did you know all of this was going to work?
I didn't.
So everything is by trial.
Well, we built, as we developed the process, we built a small little oven. Not any different than the folks here at the Mound did. I mean, you guys didn't say, oh, I know how to make tritium, and let's move on, and I know how to measure it, I know how to move it in and out. You had to do some experiments. And so that's my background, is I enjoy doing that kind of stuff. You ought to see my barn, my back barn. It's, I have a scanning electron microscope in my basement, which is kind of weird for but we do those kinds of things. It's alchemy, yes.
Yeah, when are you going to make the gold?
Yeah, there you go.
Just a question on the top coat. Is the
Yes.
top coat that they were talking about to protect that 5%?
I'm going to show you. It's that 7% iron particulate. We don't want it to blush.
Right.
But also there's another reason. In some of these, there's some micro cracks because of thermal expansion. And you think about thermal expansion between dissimilar metals, and are you going to get a little bit of crack? They're very fine, but what I want to do is fill those up with a sealer, and that's a good question.
Back to the time though, that whole process, how much time to run it? Again,
About
there's gonna be variation.
about 4 hours.
4 hours,
Mhm.
start to finish.
Start to finish. So kind of what we try to do is we'll put barrels in the oven. Like tomorrow, they'll have 4, and depends on what time I get out of here. I may go take 2 out and put 2 in, so they'll have 6 to run tomorrow. And so that's kind of what we try to do. And from an economic standpoint, if I can get to run 4, it's a pretty good margin. So we're not killing everybody, but it's a. And so these are big barrels. These are 2 meters and 3 meter long barrels. I don't have that here in Miamisburg. We have in our plant up in Holland, Michigan, we have some 2 meter and 3 meter barrels. What we have here is a 1 meter barrel. We have multiple ovens. We're getting ready to add 2 more because we've got that much work. And so they're top loaded, and I'll show you better pictures later, but there's an oven there. That's the original designs, very bulky, very big. The resistance heaters on either side as they're rotating, they're heating the barrel up. They're controlled with optical pyrometry and thermocouples. All of them have a PLC, so we can program depending on, in most cases there's 4 stages, so they'll ramp up to a certain temperature and ramp to another temperature, and then the 4th cycle basically is the door opens, they continue to rotate to cool down. Because if you just took them out right away and stopped, you'd get clumps and globs. So there's some examples of barrels.
What are they made out of?
There's steel, just a steel barrel with welded ends. So it's a piece of steel pipe, about a 1/2 inch thick. Some of them have, so part of, somebody asked about fixturing. Sometimes we put ribs inside to kind of rotate some things and keep parts moving.
What happens to the powder left over as you come down and cool?
A lot of the powder is consumed because it turns into vapor, but what's left in the barrel is a little bit of residue and the aluminum oxide. And again, I can't throw anything away, so we started experimenting. Can I use some of that used powder as a portion of what we add in with some new aluminum oxide? The answer is yes, we can. So we're recycling. These are the vibratory bowls. So they have a media in it, and ours is a plastic media. It's a little cone media. We actually use water, and it just vibrates, and the parts get cleaned with that plastic media, and it's pretty nice. A lot of the castings, we really don't need to do it because there's a rough surface on the casting anyway.
You said plastic, and in this case here, you were using ceramic. Does it depends on the specific job?
Yeah.
Okay.
Well, we don't use any ceramic. In this particular case, that was a slide we had.
Okay.
So I again, plagiarized the slide, used it, but we've kind of moved to the plastic media. It's a lot less expensive. It doesn't fracture as easy as the ceramic does. Again, this process is actually an ASTM controlled process. There's a spec for it, which was, you talk about difficult to achieve. You guys have all lived in the ASTM specification world, and trying to get something to get specified is difficult. So now the fun part, the metallurgy, the alchemy part. So as we talked about on the left, that's the thermal diffusion galvanizing, and you can see the base steel, the gamma phase, there's a delta phase, and there's a zeta phase. And the zeta phase, as you can see, is about 7% iron particulate. But again, thermally diffused down into the steel. you can see some of the same kinds of things over here. So one of the reasons we say, why is ours harder than hot dip galvanized? Well, you can see that upper layer. If you looked at, that's 31 Rockwell C hardness on the thermal diffusion galvanizing. Over here, it's not even, it doesn't even rate under the Rockwell C scale. Very soft. It's 100% zinc. Very soft, and it will, deform. And so here's an example. We talk about coating uniformity. I think there was a question. I got a couple better pictures, but you can see kind of how well that vapor gas will go into all the nooks and crannies, any open cavity. So here's my favorite one. This is the one that kind of won us some business. This is actually the recess in a deck screw. And so you can kind of see the uniformity of the thickness.
So that's where the bit goes.
That's where the bit goes, exactly. And they, I thought, some aerospace specifications were complicated. These guys, on deck screws, there's a specification that thick. I mean, there's more specifications for a deck screw than I saw on a F-14 canopy frame. So, but
What is your left picture showing here? I can't really
that's
see.
cast iron, and again, what it's showing is you can see the interface, and all these. I apologize for these. When you blow them up, it's difficult, but those are basically measuring the thickness.
Oh, okay.
And that's the same thing over there.
It's interesting, the thickness inside the corners seems to be uniform. It doesn't gain thickness as it makes that 90-degree corner.
It's because of it's a vapor. It's not a plating or galvanized. Here's some other, we talked about the micro cracks a little bit, I think when we talked about sealers. And you can see in some cases these dark areas are some of the micro cracks. Now, this one probably shows it better. There's not very many. Part of our coating development was, I don't really like those. I want to get rid of those. What can we do to the formula to mitigate those kinds of things? That happens to be ductile iron. So those are graphite nodules, those round nodules. So now let's get into the applications. We're just doing a big order up north on tie-down chains for ships, Navy ships. So we do a lot of tie-down chain. And then we do stuff that's not even sophisticated. Swing set chain. We're doing miles and miles of swing set chain. They don't want it to corrode?
Is that cost effective?
Yes. Yes. Yeah. Track bolts that you see over here. Track bolts is what Victaulic. Ever been in a parking garage and you see these big orange couplings that are holding or putting the pipes together? Most of that stuff is Victaulic's. Their idea is, I don't want to have to use 2 wrenches, so it's a track bolt with a head that recesses into the casting, and they just spin it on one side. We're working on a new coupling that they're introducing for their fire protection. I used to work for that company, and it actually was one of my ideas that they said, it's no good, it will never work. Well, after 5 years of me leaving, it's a new idea, and somebody else's idea. I reminded them, I sent them my invention record. I said, wait a minute, guys. I need on that patent too. So, butterfly valves. So the lower left picture there is a butterfly valve. And one of the things that was interesting is these butterfly valves were as part of the water going into fire protection systems. And they come out of these, lots of places, buildings have ponds. And they pump fire protection water, and it's nasty water, into their fire protection systems. Well, they would eat the valves up and they would just be destroyed. And we coated them, and it's a new one for Victaulic. So. This bottom one, and I'll show you another, I think it's the next slide. Seawall anchors. So a lot of cases where they try to keep the erosion along an embankment or a seawall. Well, what do I put in there to keep them from corroding? We coat a lot of these seawall anchors where they actually put the anchor into the side of the embankment to hold the seawalls in place. And that's again, a marine application, saltwater application, really nasty. This is one of our latest ones. These are pilings. These are pilings that they'll drill down and put them into anchor buildings. So if they've got areas where there's issues with earthquakes and what have you, they'll put these down till they get to bedrock. And so these are hollow bars, have a thread on them. They can connect them, and they drill them down, and they'll put all these piling anchors around the building. We just got an order last week for, it was 2 semi-tractor trailers of these. They're 10 feet long. There's three competitors. We're coating them for all 3 of them. They all said, no, you can't coat them for anybody else. Okay? But we do the couplings and the nuts.
Where is your huge factory here at Mound Lab?
Shh, secret. You know where the fan house used to be?
Yeah.
It's in there. That's our smaller. Our big factory is in Holland, Michigan.
And all these various applications, you base them in replacing standard galvanized stuff.
Oh, absolutely, and we're at the same cost.
How do you get the word out?
We haven't done a very good job. How's that? But once a customer, as they say, gets hooked, oh, what about this? Can you do this? Can you do that? So part of why did I want to do this? Not because Bob twisted my arm off, but is to educate people and say, hey, this is possible.
You said are these long hollow anchors?
Yes.
Down at the Holland?
Yes, they are.
Have I don't want to give any secrets. Did you find, yes, our vapor penetrates and gives adequate coating with that long aspect ratio? Or no, we had to tweak things a little bit to make that work?
It worked.
Okay.
It worked.
That's all I'm asking.
We had to run a little hotter temperature. Obviously, just like anything else, you try it. We had to section some to prove to the customer what is the thickness inside.
Yeah.
Is it, and I'm not going to sit here and tell you a fib, is it exactly the same all the way through there? The answer is no. There's some variation.
Is there just a question on that sealant again? Is that the Achilles heel at all to that coating? Because if you get through that, then you get into that iron below it, right?
Yeah, but it's iron particulate, so it may blush a little, but it's not the substrate. So this is the Miamisburg, the giant Miamisburg facility over there. So you can see how small those ovens are on the left-hand side?
We don't have any scale.
I know.
Oh, you said they're...
I did it on purpose. They're 1 meter long. Okay.
That's my scale.
But they're only about this high. Again, the barrel is about 22 inches in diameter and then 1 meter long. You can see in the background there, see the barrel? We actually created a tipper that actually dumps the parts into the vibratory table, which dumps them into a conveyor, and then conveys them into a vibratory bowl. And then it comes out of the vibratory bowl into a basket for the subsequent processes. So everything is kind of, from a lean manufacturing standpoint, we've kind of laid it out that way. And then, we talked a little bit about powder already. My other company is TDA, and it stands for Thermal Diffusion Alloys. So we've probably got 4 different alloys depending on what applications you're after. We developed it here in Miamisburg. So. Again, the advantages, we already talked about it, but lower cost, energy efficient, higher productivity, corrosion resistance, can be applied to lots of different substrates.
What kind
kind of traceability do you have in the process? Do
So-
you, every time you're running a batch for a customer through, you record temperatures and times?
Everything
and all this
is,
stuff?
the answer is yes. And how it's done is, so for example, we load a barrel. And Gabriel can tell you, he made a mistake once, only once. And so now what do you have to do when you put powder in and do everything else?
You have to check the, them with the alcometer. And if
No,
they're-
before that, when you're loading the barrel.
Oh.
Put powder in, what do you do?
Oh. I don't know. I can't remember the day.
He has to initial,
Oh, that's right, yes.
he has
That's
to
the sign
initial
sheet.
that particular area. How much powder did I put in? How much aluminum oxide did I put in? What oven did it go in? How many pieces were in it? What type of piece was in there? Dates, times. And then the PLC in the oven actually controls the process, so we can go back and say, oh, wow, it came out thin. We had one, he forgot to put powder in. So we're checking it, we're going, whoa, wait a minute, this is not right. He remembered, oh, I forgot to put powder in, so we changed it to initial, I put powder in. So those are, and then we can actually create a cert that we can ship with the parts that they would like. That we've checked it, because then with the alcometer, we're checking the thickness, multiple locations, 2 pieces out of a barrel. So that's what we do.
What temperature range are you talking about for the creating the vapor?
It depends on which powder, but we can go as low as 350 degrees centigrade.
You're not in any danger of changing the properties of the steel like or
Good question. One of the things that we did is on those fasteners and deck screws, they would actually temper them, okay? And I said, you know, our process temperature is right there with your tempering temperature. And I started thinking about it. I says, why don't we just temper them in our process? So that's exactly what we did, is we killed 2 birds with 1 stone. We said, oh, we'll coat them and temper them for you and save you the additional operation. So, worked out pretty good. But it took a lot of alchemy and metallurgy and fast talking to convince them that I knew what I was talking about. They didn't believe me. So we had to show them all the data. Okay, there it is. So these are the top coats in a little bit more specifics. The Ultraflex, which is the silicate based, and the Ultra Nitra is a water, and it's more of a chromium nitrate, and that's why it's called Ultra Nitra.
Yeah, I wasn't being completely facetious. I was thinking that you have an understanding of how these chemicals are going to react with the temperature with the metal, and you haven't said anything about that.
Well, it's one of those ones where I understand the physics of it.
That's what I was asking.
Yeah, I understand the physics, and so that's where, when I wrote the proposal that I would develop these powders, I had an idea of what has to happen, what do we need to do, what do we need to try. We were able to try some of those things. We built a small little oven this big that rotated and did everything. We used nails, put nails in there, and we coated and worked on the process. And then, you know, I told them it was going to take maybe 6 months to develop it. You know, some of my ideas worked, and in a couple of months we had a formula that we said, why don't you try this? So, did you have a question, sir?
Yeah, when you have nuts and bolts and you're torquing them up to certain specs, does this affect the coefficient of friction? So this affects.
Actually makes it, improves the coefficient.
Yeah,
of
but that's going to lower their torque then for pulling the
Yes.
bolt up to a certain temperature,
Yes,
right?
yes.
So that has to be taken into
And
consideration.
it's a good thing
Yeah.
in a lot of cases, yeah.
Does that help the surface for, keep it from spalling and everything?
Yes,
as they're tightening?
it doesn't spall, yes. No, that's a good question again.
Does it help us prevent stretching the threads too?
Yes, because it's harder, yes. Now, granted, if you can imagine, here's a nut, right? If I add thickness to both sides of that nut, I go to put it on a bolt, If I don't oversize the nut a certain amount, they do that with wall coatings. It took a lot of convincing to some of these, oh, no. And actually there is a study that, if you're interested, I could share it with you, where we actually went through and said, what's the torque and the strength of that fastener with oversized threads in the coating. So, okay. Well, we've done a bunch of questions already. And I appreciate the questions, I really.
The symbol up there intended to convey, is that just, this is a green
Yeah,
process?
green process.
Okay.
Mechanical and green.
Yeah, all right.
Any other questions? Anything else we didn't delve into?
Well, thank you, Jim.
You're welcome.